You're welcome once again to another fascinating math video. In this video, we shall be considering a rate of change problem. And before I go over to the solution of this problem, I'd like to inform you that I offer a private online math tutoring service for the primary level, secondary level, and to the college level. Any of these levels, I'm very qualified tutor for them. All right, so be very free to get across to me if you're in need of such a service. So we want to look at the solution to this problem on the board. It is a rate of change problem. It says over here that if the function f, now if you want further studies on function and properties of function, you make your comments on the video, all right? Or you can message me directly for a private tutoring service so that you get more knowledge on functions and their properties. There are different kinds of functions. So let's continue the problem. If the function f is defined by f of s equals to square root of x, find the instantaneous rates of change of f at the point x equals to 1 from first principles. So we have to solve this problem from first principles. We have to find the instantaneous rate of change of f at the point when s equals to 1. All right. Now let's go over the solution of this problem. Solution. Now, according to Joseph Louis Langridge, the rate of change of a function is denoted by the prime notation. So if we say f prime of x, this notation denotes the rate of change of the function f with respect to x. That is according to Joseph Louis Langridge, all right? And is defined as the limit as the quantity h approaches 0 of a difference quotient of the function, which is f of x plus h minus f of x over h, all right? This expression within the Coiling parentheses is called the difference quotient. So when we take the limits of this difference quotient as h approaches 0, the value, if the limit exists, because there's something for a limit to exist, all right? It then follows that we cannot just draw tangent to the curve. You are not free to draw a tangent to a curve if the limits at that point of the difference quotient does not exist. For you to draw a tangent to a curve, the limit of the difference quotient must exist, all right? So when you take the limit of the difference quotient, what you get in return is the instantaneous rate of change of the function f, all right? So what we shall do, we shall form the difference quotient. Now, we are to look for it at the point where s equals to 1, all right? So that means this will become f prime of 1. Instead of x, we'll put 1 there. And this is equal to writing the limits as h approaches 0 of f of 1 plus h minus f of 1 over h, all right? So we have an expression, a beautiful expression. So we want to modify this difference quotient to be amenable to the approach, all right? So what we shall do, we shall bring it out separately. I can call this expression over here star, all right? Let me call it star, for example. So if I bring this out, I'll be having f of 1 plus h minus f of 1 over h, all right? And this is equals to writing. Now, from the function is giving us f of x equals to root x, all right? Where s is a pre-image, or you call it the argument. Now, if you observe carefully, we are having 1 plus h as a new pre-image or new argument. And this 1 plus h is supposed to be in the domain of the function f. So that means if f of s is root s over here, we shall have our f of 1 plus h to be root 1 plus h, all right? The minus. This f of 1 will be f root 1. Can you see that? Or divided by h. This is a difference quotient, all right? Now, let me come over to this side of the board. We want to simplify this. This is equal to writing the root 1 plus h. Now, root 1 is 1, all right, over h. Can you see that? So you may suggest, okay, let's substitute this difference quotient within this parenthesis in star. If you do that, you will run into a problem because in taking the limit when h approaches 0, we shall have our h here to be 0. And division by 0 is meaningless, so it's not defined. So how do we go about this? We have to modify this form, if possible, so that we can get the limit without dividing by 0, all right? So how do we go about it? We shall do what's called the rationalization of the numerator. Now, how do we rationalize the numerator? If you observe carefully, this is solved. we have root 1 plus h minus 1. And the conjugate of this expression is root 1 plus h plus 1. All right? So, and you know that if a sword is multiplied by its conjugate, that is the results become a rational result. It become rational. So we shall apply that knowledge here. So the conjugate of root 1 plus h minus 1 is root 1 plus h plus 1. So in that case, I can write this as being multiplied by root 1 plus h plus 1 over root 1 plus h plus 1. Because this divides out to become 1. And 1 times any expression leaves the expression invariant. So because of that, I can do it like this. All right? So this can also be written. Now, when this multiply this, we shall have a very simplified form. Now, don't forget, from algebra, we have a to the power 2 minus the second power of b. It can be written as a minus b multiplied by a plus b. All right? So if you observe this expression here, it's exactly the expression we're seeing in the numerator. This root 1 plus h minus 1 is multiplying root 1 plus h plus 1. All right? So in this case, our a is denoting root 1 plus h, all right? While our b is denoting 1. So this expression, they are parallel. They are parallel, so they are the same. So that means we can reverse from the right-hand side to the left-hand side. Can you see that? So on reversing, we have the result as root 1 plus h to the power 2 minus 1 squared over h. Can you see that? All right? And this can be written as 1 plus h minus 1 over h. From whence this we cancel out, or we omitted something. Look at this denominator. This times this gives us this, all right? That is, when you multiply this expression over here by this expression over here, you shall have this result over here. Can you see that? The same thing, the denominator times this expression at the denominator, you have it as h multiplied by root 1 plus h plus 1. Can you see that? That means I will have to add it over here. Sorry for that, it's just an oversight. So we have this as a result. Can you see that? Now, this h we cancel out with this h here. We have the result as 1 over h root 1 plus h plus 1. Sorry, it will not be here again. Yes, we have it like this. I think this is the right thing to do. This cancel out. And h divides out h, it become 1, all right? So we have this expression, and this expression does not contain h at the denominator. That will result to divided by 0. So this is a very good form. So this form of the difference quotient will be substituted into star. Look at star over here. Don't forget it's star. All right? This expression here. So this f prime of 1 equals to the limit as h approaches 0 of this difference quotient. And this difference quotient has been simplified to this form. So in the place of this expression within the coiling parentheses, we can put this form. All right? So in bringing it, we have that our f prime of 1 is equal to the limit as h approaches 0 of, instead of this now, we put 1 over root 1 plus h plus 1. All right? Now, and if root 1 plus h should approach 0, if h should approach 0, root 1 plus h will approach the root 1. All right? So in that case, we have it as 1 over root 1 plus 1. So in this case, it becomes 1 over 1 plus 1, and that is 1 over 2. So that means that the rate of change of the function at the point where s equals to 1 is 1 over 2. All right, so we have come to the end of this video, guys. Do me the favor to share the video, comment, and also like the video if you draw any value from it. Don't forget also that I offer a private online math tutoring service for kids in primary level and secondary students, also for college students. So if you need of this service, be very free to get across to me. Thank you very much for being with me tonight. Thank you.